So today we are going to talk about suffix tree using Ukon's algorithm. Suffix tree is a tree which consists of all the suffixes possible of a string. For example, if we have a given string xyz x dollar, then we have the first suffix as the string itself xyz x dollar. Then we have yz x dollar, then zx dollar, then x dollar, then dollar. So suffix tree will be a tree which consists of all these suffixes. Let's see, this is the suffix tree. For example, we have xyzx dollar, yes. Then we have yzx dollar, yes. Then we have zx dollar, yes. Then we have x dollar, yes. Then we have dollar. So we have all the suffixes possible. So this is basically a suffix tree. And Yukonen's algorithm does this in a linear time complexity that is big O of n. So we will see how we'll go about this. We are going to see in the upcoming time, and there's a lot of applications for it. That would be the last part of this presentation. Let's see. Moving to the Yukonen's algorithm, first we'll see a algorithm with a runtime complexity big of n cube. So that now from then we can see what all optimization to make so that we have an algorithm which runs in linear time. So we'll have two variables I and j, and I will denote the phase, j will denote the extension. So we have to remember these two rules. Rule 1 says we add a character to the path, and rule 2 says we create a path if it's not there. I'll explain it with example. Let's say if the string is given to us is this, so our I will start from here, j will start from here. So as we don't have, this is our root node, as we don't have any character with the then we can't add character to the path. So by rule 2 we create a path. So we'll add x, then our phase is over, we'll move on to next. Our phase moves to next, but our extension will always start from 0. So now our phase is currently here. Okay, so by rule 1, first we will add the character to the existing path y, and by rule 2 extension we will add x, we will add y, we'll add y, because now this also comes from here. I will not use the variable so that you don't get confused, but that was just to explain you the phase and the extension part. Okay, from now on we have come here, our phase is here. So first we'll add x, y, z. By rule 1 extension we added a character, and when the extension moves here, yz. Now by rule 2 we'll add the leaf. Now moving on to the next phase. Extension again starts from here. So x, y, z, x. Then by rule 1 only we are doing this, y, z, x. Then dx. But now in this particular case, by rule 2 extension we say create a path, but from the root node we say x is already there. So what do? In that case, there is rule 3, when we don't do nothing and move on to the next phase. So in this case, x is already there, we'll not do anything and we'll move on to the next phase. Rule 3 is basically a stopping criteria. Again, the extension starts from this, Now by rule 1 we'll keep adding in all the paths. And now by rule 2 we'll, now as you see, last time we didn't add here, we are done with here, but now as J and I comes here, basically this is J, this is I, from J to I, X is there, so we'll increase our path here. Okay. Now again J and I at the same place, so we'll have dollar. By rule 2 extension we'll create. I hope you must have understood by now what is happening. In the next phase, then starting here, A, then this A, then this A, then this A, then this A, then again A by roll to extension. Now this, I should remove this, otherwise it will be cluttered. Now we'll add by rule 1 extension, we'll keep adding Y, Z, X dollar X, AX. Now we have X here, so we don't need to do anything. Move on to the next phase. Y, by rule 1 we are adding Y, X dollar XA, X dollar XA, Y, then AXY, then we have AXY, then we have XY we already have, so by rule 3 we don't need to anything, we'll move on to the next. B, we have B, 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 sorry I forgot to add it's in my here, and then we have B, and then we already have in this case AXY, so B, and then by rule 2 we already have XY, so we add B. So basically I did it a little faster because I'll go slowly in the main algorithm. This was just to give you an idea that each time if we have this as the length of this is n, our I and j will have a time complexity of big of n square, because they will run big of n square, and they will run for n time. Basically for each phase, n phase, then we have n extensions, and then this will happen for n times. So basically this is a big of n cube, or you can say what people say, big of m cube, basically where m means the phases. Solution. So now we'll see the main algorithm, and we'll do that slowly, like what is Buchanan's algorithm and how does that runtime, how does that algorithm have a runtime complexity. Okay, so now we will see Buchanan's algorithm, which is a linear time solution, and we will follow all the rules which we have seen previously, those three rules, and these are the variables, and we will see, understand this algorithm with the help of an example, and I will tell all of these variables on the go as I explain the example. So first we'll create a root node. Now default end value is -1 and remainder value is 0, and I will denote the phase of the algorithm. So we'll start. First we go to 0. We'll increase this by 1. We'll increase the, as we change the phase, we increase the value of the remainder by 1. So we'll take. By rule to extension, if the leaf node is not there, if the path is not there, we'll create the path. Now, as we created the leaf node, we will decrease the value of remainder. Now, as the value of remainder is 0, we will come out of the value and we will go to the next phase. Now, in the next phase, we will increase the value of the end variable and the remainder variable. As we change the phase, each time we will increase the value of remainder and end variable by 1. Increment by 1. Also, I forgot to tell you, we will not keep the path, we will not keep the character, but instead we will keep the range. This is just to show you. Okay, so by rule 1 extension, we add the character to all the paths present. By rule 2 extension, if the path is not there, we create it. Now, as we create the leaf node, we decrease the value of the remainder. Now, as the value of remainder is 0, we'll come out of the loop, we'll go to the next phase, and this is how it will keep going. Again, by rule 1 extension, and by rule 2 extension, we create the leaf node because n is not there. Sorry, I forgot to keep this. And now we'll go to the next phase. We'll increment the value by 1. By rule 1 extension, we add it to all the paths. A. Now by rule 2 extension, we can see the path is already there, A is already there. So what we will do, in this case, we will go to rule 3. If the path already exists, we just increase the value of, we just change the active node. Basically, earlier active node was A, default all these values was A and 0, 0. So as now, we don't create a new leaf, what we do is, we change the active node. Our active node becomes this. So our active edge value becomes 1. Our active length also becomes 1. And now we can go to the next phase. Basically, we go to the next phase only if either remainder is equals to 0 or we use the criteria 3. If we have used the criteria 3, then also we go to the next phase, but we don't decrease the value of remainder. So now we go to the next phase, increase the value. Okay, so now we again add all the values by rule 1 extension and now we by rule 2 extension we see if n is there. Yes, n is there. So again what we'll do is by rule 2, as we can see we have n here, so rule 2 is not applicable, and by rule 3 we increase the pointer to n. And now we'll go to the next phase as we have implemented rule 3, which is again a stopping criteria. Now by rule 1 we'll add a to every path. Now by rule 2 we'll see, yes, a is there, so we can't add. We need to again go apply rule 3. Now we have used the stopping criteria rule 3. Now we'll go to the next phase. So by rule 1 extension, we'll add the character value to all the parts. Now we'll see by rule 2 extension that after the node do we have dollar, do we have a leaf, we don't have, so we'll add. We'll create a node here. Suffix links will point to A because that is the root node, and now we decrease the value of remainder because we created a leaf node. Now as we see, our remainder value is still greater than 0 and we don't have anything to do. Now we'll increase the value of active edge and decrease the value of active length. So from node A, our edge value 2 become here, then our length value 2 become at here. So now do we have dollar here? Basically our current phase we don't have. So we'll create one more node in the same phase. As we are creating the node in the same phase, now this suffix link will be, this will point to root and up. And a previous node will, suffix link will point to this. And as we created a leaf node, we will decrease the value of remainder. As you can see, we still have an active length, so we will increase the value of edge. and decrease the value of length. Now from the node A, we'll go to the edge 3. Can we see edge 3? No. Active edge is 3. So we'll go to A and our length is 1. We'll create a node here and we'll create a leaf. Again 6 to end. We'll decrease the value of remainder. As we are creating the same in the same phase, now this will point to D and C will point to this, our suffix link. Now we are still not done as our remainder value is 1. So we increase the value of, we increase the active edge to 4, decrease the length to 0, and now we will go to active edge 4 meaning n, length is 0, so we'll click this only, we'll create one more dollar. Sorry, basically our active edge is here, active length is 0, so we'll create here only after n. So now as we created this, we'll decrease the value of remainder by 1, and now we'll create our, as our remainder 0, we'll create our final output, last one, and we'll come out of this finally. So now we want to see whether we have all the suffix or not. So we see B, A, N, A dollar. Yes, we have that. Now A, N, A dollar. So we A, N, A dollar. We also have that. Now NA dollar. So we have NA dollar. We also have that. Now A dollar. So A dollar, we also have that. Now NA dollar, we also have that, and then finally A dollar, we, as you can see, A dollar, and lastly the dollar itself. So as you can see, our suffix tree was done in only one for loop. So the time complexity of this is big O of n, and we have created all the possible suffixes possible of the given string. We have all from the root node to the leaf node as I shown you. Now we'll see the application of this. We'll see the application of the this suffix tree. So first application is a substring search. The question will be, we'll be given a string and a substring for it, and a substring, and we need to return a boolean value whether the substring is in the given string or not, true or false. So I have already made a suffix tree for the clarity so that it doesn't get messy like the last time. So let's see an example. For example, we are given a substring A, B, X, and we need to return whether this is present in the given string or not. Substring is basically a prefix of a suffix, so we can easily from the root go to the leaf, and if it is there, we can return true, otherwise we will return false. Let's see. So ABX, we know that the answer for this needs to be true, so we'll go to the root, then we go A, then we go B, and we go X. Yes, it is there, and we return true for it. And now let's say something different, XAC. XAC. So again we'll start with the root, we'll go in direction X, A and C. Yes, this is also there, so we return true. Let's see an example in something which is not there. X, so we know this should return false, so we start from the root x a c, no, x a b, so yeah, we can return false for it. So basically we have to just go from root to node, a leaf node, and if the path is the substring is there, this will suffix tree will contain that. So this was the first application of suffix tree construction. Now we'll move on to the second thing. The second application of the suffix tree, longest common substring. So if we are given two strings s1 ab ab b ab a, we'll join them with a different sign ending to post to it. Like first string we use dollar sign, second string we use hash sign. We make that string, then actually in the problem we need to return the length of the longest common string, or maybe the string itself, just not the length. So we'll make a single, we'll concatenate the two strings, we'll make a single string, then we'll make a suffix tree. For example, we combine these two and then we made a suffix tree. So I've made priorly to it for the neatness of it. So root a b, and in this node we will denote 1 and 2 when the value from both the nodes are present, when both the strings are present. For example, dollar and b because of both, s1 and 2 dollar and because of both. If for example this can also be s1 b or s2 a. If the value on the node is not present from both the string, then the value present from the string itself only represented. As long as both the string have the value, that will be represented. So once we make the suffix tree, then it's very easy for us. We just need to see which is the longest path. Basically, we'll go top down. It's a recursion, standard recursion question. So we can see a, b, a, and if not, we can go there b, a, b. Basically, both have the length of 3, so you can choose any of that, because as both of them have the strings. So basically, you just need to make a suffix tree. Then it's your normal recursion question of calculating the max length, so which can be done in big O of n itself. So this is the another application of very popular application of the suffix tree. So I have covered the application as well. This would